I think we will start. Is that okay? Yeah, okay. Thanks everyone for coming. It's great to see that a lot of people came so early in the morning, still drinking your coffees. My name's Rezaul Hoque. I come all the way from Europe. I work for Microsoft, and today we'll be talking about powering 100 million users daily. A bit about me. I work as a senior software engineer at Microsoft. Have been working there for more than 8 years now. I have been part of the core team member building the Microsoft Office graph, if you are familiar with it. That what I did in that project was mainly focus on the storage, on how we store user relationships on disk so that they can be queried in an optimized fashion. There's lots of interesting stories around. Okay, this actually jumped over. Yeah, so there is a lot of interesting stories around that. But today we are going to talk about something else. In the last 2 years, I've been working with a team where we build people experiences for Microsoft as Office 365 offering. How many of you know about Office 365? Can you raise your hand? Okay, that's great. Okay, do you use it? Okay, that's also good. So at least we will talk about some experience that you already use. So I've been a tech lead for a few of the services which powers these experiences in Office 365 across all the workloads, from Outlook to OVA to SharePoint to OneDrive. So what do we want to do? For example, the core mission for Microsoft is that we want to empower people to do more at work. This is why Office 365 exists. This is why a lot of productivity tools exist today. And our team wanted to looked at it and said, when you want to communicate with a person, you can chat, you can call over Skype, you can collaborate through slides, documents, and whatnot, right? And I guess a lot of you do that on a daily basis. But you also talk to your clients which are new. You don't have no idea who they are. You also sometimes talk to your manager or a person who's new in the company, wants to know who you are, what you have worked on. So you want to be able to contextualize the person when you're working and collaborating. So that's what we wanted to build. We wanted to build an experience where you could have a 360 view of a person and understand immediately who this person is, how can I reach him, what kind of things is he or she working on. So the experience that, this apparently jumps, okay. Yeah, so this is the experience that we kind of went and built and which actually captures all this information for you. To be able to actually power this experience, you need some set of data, right? And luckily for us, in Office 365, all these workloads already have this data. It's present. The challenge, however, is that all this data about a person is fragmented across all these services. And each of the services have a different availability requirements. It has different performance. Some of them are slow as a couple of seconds. But if you want to build an experience where you want to see who this person is before you start chatting with someone, you cannot wait for seconds. Worse, if you aggregate all over these 10 data sources, the slowest one is your bottleneck, right? So you needed to build an experience which is fast enough, still yet have the same data from all these data sources. So that's what we will talk more about today, on how we build that service to power this experience. A bit about how it looks now. If you actually go to Outlook today and you have your emails, and if you click on someone, you'll be able to contextualize that person. You get this kind of a view, right? Where you're able to know how to contact this person, how to reach that person, what kind of files he's working on, what kind of LinkedIn view does he have, where has he worked before, and what are the documents that you both are collaborating with each other now. So this is a feel of the experience that we have built. So we want to talk about goals, high-level goals that we wanted to achieve because of this. One is that we wanted to build a service which will power this experience, and it needed to be scalable, right? Because we knew upfront that if we have to ship this to all these Office 365 workloads, then it will have to serve 100 million daily users. So we need to build the service in a way that is scalable. The second thing, we need to ensure that this view that comes, it's super fast. And we'll look at some of the things that we did to reach to those goals. And lastly, while you actually go and build a lot of these services, you actually add more and more engineers, it becomes successful, teams grow, people grow, code base grow, right? I think we have realized over and over again that we do not put enough thought on how we are structuring our code. So I'm going to talk a bit about that space as well and what we did there and what worked for us. Let's start with scaling the overall architecture. Let's take a very simplified view of how it looks today. This is a very oversimplified view of our architecture, but I think this kind of captures the main things that we need to scale. So on one hand, you have the experience that you want to power. On the other hand, you have all the data needed to power that experience, right? Spread across many data services, as I said, like LinkedIn, AD, OneDrive, SharePoint. And you need to basically bring all this data together, reason over all this data, aggregate them, use some ranking algorithms to rank what data is useful for the person who's looking at it, and then serve that data. So you need a service. And then you build this middle tier service, and you basically fetch all this data, and you show this experience. The problem is, however, that as I said, the data services were not fast enough to give data back in a responsive way. So what do? We just like add a cache, right, on top of it. So very simple architecture. You build a service, you put a cache to make sure that you have your data sources, the data needed available in the cache so that you can actually do the needed processing and serve this experience. So if you look at it, the main 2 or 3 things that we need to scale for this entire architecture to scale is that you need to make sure that your middle tier service is scalable. You need to make sure the Redis cache that you're using is scalable, and all the data sources that you're talking to, if you put more load to them, they are scalable as well in addition, right? So that at least these 3 things that you need to make sure that they're scalable. So you need to ensure that the compute that you have is scalable, the Redis you have is scalable, and the data service that you are using, all these resources are scalable. Does everyone know what Redis cache is? Yeah, there's a lot of nodding heads, but for people who do not know, it's a simple cache. It's a network attached in-memory cache. It's something that Azure provides out of the box for us. It's managed, so you don't have to host a VM and then run it for yourself. You can just talk to it, and it will manage it for you. If you look at this, the first thing we did is that we went to all these data services and said, okay, we are going to put this much of load on you eventually. Can you handle it? And the answer was yes, with some caveats, right? So we are not going to talk about those. But it's important to realize that any dependency that you take, you need to make sure that they are scalable, or else your overall architecture is not scalable. Then we looked at our compute and we said, okay, we have this service. We need to make sure that when we have more users, that needs to scale up. How do we do that? These days, it's very simple to do that, right? If you have a stateless service, all you do is that you pick your cloud provider. For us, we picked Azure, understandably. So Amazon Web Services have the same capabilities as to just get a compute, and then you say, I want to auto-scale this when load increases. And that just happens out of the box these days, right? So there's no magic there, so we don't talk about that today. Cache, however, is a bit tricky. It can be tricky, because for us, that is one of the resources which will grow over time as we become more and more successful, as long as we understand our scenarios better and cache more of the data, because it actually helps build the right experience for us, that will grow. So we knew that. And today, Azure actually provides a premium version of Redis cache. If you actually pay more, you get scaling out of the box. Even though we are Microsoft, we kind of said, yeah, it's expensive, right? Can we build and scale it ourselves? So I'm going to talk about how we did that. We kind of, in this picture here, you can see that we have the VM or the virtual machine and the services there. And on the right-hand side, you can see we have like 4 instances of Redis. And each of these instances have around 56 GB of space. And what we want to do is that we want to cache across all these instances that's running here. So we need a way to partition the data uniformly across these instances. So let's say, for example, like a user comes and looks at someone's card, and that call basically ends up to our service. At this point, you have a unique cache key. You have formed that this is the piece of data that I want to store in my cache. So what we do is that we go ahead and do a hash. We do a consistent hashing on the key. If we do a consistent hashing on the key, it has a nice property that it uniformly distributes the output for you, right? And it's also one-way hashing. So every time you have the same cache key and you do a constant hashing on that, you get the same number. We take that number and we do a modulus on the number of instances we have. In this example, it would be 4. So you do that and you get a number out of that from 1 to 4. In this example, let's say we ended up in Redis 01. So remember this, that we ended up for this cache key on Redis 01. And if you do it again, you have the same cache key, same constant hashing, same modulus of on 4, you get the same number. So it's sticky, right? So you get to get back to where you have stored it. And because of constant hashing, you have redistributed data uniformly across these 4. This 4 fills up, you have more users, you're more successful. And now you want to add more capacity to it. So what you do is that you just take out of the shelf and add one more Redis instance to this configuration, right, to topology. That's super simple. One click away, you get one more up. But now what will happen is that you have updated your code and say, there are 5 instances now. You do the same thing. You come, we have the same cache key. You do same constant hashing. You get the same number till here. But now you do a modulus on 5 instead of 4 because you have 5 instances. And that means that you will get a number from 1 to 5. And you will not necessarily get 1. There is a probability that you might get 1 as well. Then you might end up in the right instance. But there is a good probability that you will end up in some other because now your distribution is different. In this case, this is a cache miss. So what is important to note is that if you use this scaling strategy, you need to make sure that you can tolerate cache misses. That when you scale up, you will get some cache misses. In our case, what will happen if there is a cache miss, we'll just go back to the downstream service and say, hey, I don't have it in the cache, can you give it to me, right? So that works out for us. If you actually had persistent storage, then this model will not work. You like kind of lose data, right? So you have to make sure that you can use this scaling model only when you are able to withstand some loss. If you actually had a persistent data storage instead of cache, you had storage and you wanted to use this, when you add one of these new storage, you have to go and repartition your area. You have to move them around. And that's a really harder problem. And that's some of the harder problems that, like when you store data, you have to solve. Yeah. So now let's look at, so we talked about this building blocks, like, oh, we are scaling up our compute, we are scaling our Redis, right? So we take almost all our resources that we have, we bundle it, and we deploy them in one data center. And we say, okay, this is great. Like we are serving all this experience from this data center. But let's say that that data center does not have capacity. It doesn't happen that often, has happened to us a couple of times. So we kind of said, okay, if that data center does not have capacity, maybe another data center has capacity. So we took the entire thing and replicated it in another region, right? In the same geography. We did it for a couple of reasons. One is that if you are in more regions, that means people who are living in East US, you have a data center there, your code is more closer to them, therefore it's a bit faster, right? The network hop is closer. The other reason why we did is that we have this ability that if something goes wrong, it often doesn't, but you have another thing to fall back on. So you have a disaster recovery scenario, you have more availability scenario. If you guys follow Azure, who knows that Azure South Central US was down this month? Okay, great, yeah. So this actually happened, right? Like there was a lightning strike. There is actually a very nice write-up. Microsoft like did a very detailed RCA, like root cause analysis on why like a simple lightning strike could take an entire data center down, even though we have a lot of fail-safe. We have a lot of fail-safe in the data center. It's not that you trip a wire and then everything goes down, right? They have a lot of fail-safe in every data center. Amazon probably has the same. All cloud providers have the same. Yet these kind of things happen. So if you were only in South Central US, because all your users were there, you'll be completely down, right? So this happened to us. And with this setup, with the traffic manager on top, our traffic just got redistributed to the other ones. Because we have a lot, so it was almost not a headache for us. But we did see the blip in our optics that, oops, something went wrong. And we were like, oh, we did something wrong. And we went ahead and said, okay, great, it's not us, right? It's Azure. Azure is down, so it's good. I think this kind of setup really helps you in those kind of cases when this actually happens. Even though it doesn't happen that often, it's good to have this kind of setup. Now it could also be that the entire geography, entire US could be down. I mean, very highly unlikely, but who knows, right? Like, with all these geopolitical things happening these days? No one knows. So you go and actually take the same concept and build more data centers or stand up your code in more data centers in more regions across the world, right? Like you have Latin America, you have Europe. You do this for two reasons. One, you want to be more closer to your user so that you can serve faster. And you also have this geo availability zones where if half of the world goes down, your experience doesn't go down. I don't know if it really makes sense to see a card if half of the world is not there, but we will be available, right? So it's like fun. Was there a question? No. Okay. Yeah. So, and if you think about it, we started with simple building blocks. We ensured that each of them can scale. We took all of them, composed them together, and then we scaled in a region, and then we scaled across geographies. Now we kind of are everywhere in the world. This is a very nice map of Azure, where it shows all the regions that Azure actually has a data center, and or some of them are upcoming data centers very soon. We kind of like look at this usually and look at the traffic pattern that we have currently and where are our users located, collate those two information and say these are the places where we need to be. And I think I would encourage a lot of you not to just blindly build and deploy your data centers all across the world, right? The thing is that you should know that you want to be in more than one region, in more than one geography, so that you have this fault tolerance, and you can scale out of the data center, but also try to be in places where your users are, which will actually help you. Okay, so we talked a bit about scaling. Now let's shift gears and talk about performance. So we want to have, we kind of say, oh, we want to have support blazing fast person card, right? We want to like whenever you click a person, it should come instantly. But what does that really mean, right? Like when you go to the crux of the problem, there is this notion of user perceived latency. How many of you are familiar with this concept of user perceived latency? Okay, couple of hands. But what it actually says is that it's not about just serving everything very fast. What matters for the user is that he or she sees something on the screen that they can start consuming while the rest of the thing loads. If it's like a white page for like 3 seconds and everything comes after that, it's not that good. If some parts of the card which are important, like for example, if for news, if the headlines and the picture comes, then that's the first information that the user is consuming, and then the rest of the news can come, right? So we looked at our experience and says, what does user perceived latency mean for us? The experience would be that you get the card, and then you get the rest of the card. And we believe that if you can see the first part of the card, you have actually contextualized that person enough to be hooked to stay for the rest of the card to load. And therefore, we put some perf requirements for ourselves, and we said, we want to be able to render this top part of the card in 250 milliseconds, end to end. That means starting from the browser, getting all the data out and rendering it, right? So that's like end to end perf number that we want to achieve. And the rest of the card could render in 600 milliseconds. Then that's okay. And that's also pretty hard to do, but I think we'll focus more on the top part. Let's again look at the architecture we had. We said we have a service which basically takes all this data out, does its magic, and then serves the experience, and we put a cache so that there is no delay, at least fetching this data. Imagine you have this architecture, and I go and click on one of my colleagues. The request comes to the service. The service basically looks up the cache. There's nothing in the cache when it's the first time you're looking up. You go fetch all this data, do it. It takes a few seconds. Yeah, I'm not really happy. I'm never using the card. Like, what do I do? Because but if you had clicked it for the second time, then it comes to the service, comes to the cache. You get a cache hit. It's instant. But does it really matter if the second time is instant? It doesn't, right? Because when I really need that information was the first time when I wanted to contextualize. I don't want the guy go and populate your experiences cache so that next time I can actually use it. So what I'm getting at is that this cache is there, but you need to make sure that the cache is populated beforehand, before you actually need it, somehow. So we do something called prefetch cache, which is a standard technique, I would say. And if you look at our experience, let's say we take Outlook. The picture looks really bad here. Bad resolution, but it's not that bad. I guess a lot of you use Outlook, so you know it looks great. Uh, so, for example, I think at least we'll get the idea here that you load the card, and then you have a bunch of people in the card, like people who send you emails, conversation threads, and you will be able to click in any of this person and say, who's this person sending me emails? Like, what is he working on, and stuff like that, right? That's the goal. The good thing over this is that none of you, I hope, open Outlook and immediately go and click on someone. I don't want to care about email. I just want to open and click, right? It doesn't happen like that. So most users like open, maybe it takes a few seconds to gloss over the experience and then wants to say that who is this person. So those couple of seconds are super important for us. What we do is that in that couple of seconds, we kind of figure out all the people which are visibly rendered in this page, and we can just send a prefetch signal saying that, hey, you know what? Someone might actually click on this person to know who this is. So go and prefetch this and go and cache it. And then we solve the first bootstrap problem for this user, right? So now when I go and click on someone, I get an instant card because that was prefetched and cached. The probability is very high for that to happening. And we have seen in our system that actually works for us. We have a cache hit ratio of around 93% now. At some point we had 98, I don't know, we regressed a bit. But 93 is pretty good. And our ambition is to be at 99. We are working on that. So if you look at it, what we did is that we just looked at our scenario, we took a simple heuristics, and then used that to actually prefetch and cache. But there is also a lot of resource waste on when you do prefetch and cache, right? I want to highlight that. You had like 50 people, for example, in that page. You prefetched and cached for all these 50 people because you thought they might click, and you don't want to be slow when they click. But maybe the user just clicked on one person, or maybe 5 maximum. Didn't click on all 50 of them for sure, that we know from data. That means the data that you did not click are all wasted. It both wasted my compute resource, it wasted my cache resources, it wasted some resources downstream for those services to actually give me that data. So now we are starting to use machine learning models where we can predict, based on all the people that you interact with, who are the people who are very strange to you. So you have no idea who these people are. And then the probability for you actually going and trying to know who this person is very high. So then we kind of like group them, and we say, hey, like out of this 50, if you can fetch only these 15 people, then we know based on the data from before that the likelihood of them clicking is more than 90%, for example, right? This is a hypothetical example. That means you can remove the rest of the 40 people and not prefetch and cache for them, and take the hit. If anyone happened to do it, then we are slow, but then the machine learning model basically learns, and over time it becomes better and better. This allows us to become more efficient. So you have the cache on the service side, let's say, but then, and to get the cache, like from the service to get the cache, it's single digit milliseconds. You can, if you want to read something from Redis cache, it's like 2 seconds, 3 seconds. Maximum it takes 9 seconds, I think maximum that I've seen is a single threaded model. It's pretty good, very efficient, right? So that's not a bottleneck. So now you just spend, let's say, 5 milliseconds here, but then you have to send the data back all the way to your client, right? So what you do, just do a simple REST request. What can go wrong? Like, remember that we have this 250 millisecond goal, and we measured it, and it's 600 milliseconds in between. I was like, okay, what's happening? There's something happening behind the scenes, right? You are using an HTTPS, so you do this 3-way handshake to form the secure connection, TLS, and all that. So it turns out it's pretty slow. It, like, just to send that data back, it's 600 milliseconds on networks which are bad, and we are not able to meet our goal, even though all the things are cached on our server side. And of course, there are monsters in the internet as well, right, which drags everything down, right? That's there. It's the truth. So now what I'm getting at is that to be able to transfer this data all the way there, we need to reduce this TLS handshake. But you also still need to be secure. So one way to do that is to use a tunnel, right? Like you can use WebSockets or SignalR or whatnot to form this tunnel. While you're forming this tunnel, you do this TLS handshake and you form that connection, but then all the other requests just tunnels through it. We kind of chose to go with SignalR. It was very easy to start with. Have you guys used SignalR? Oh, lots of people use SignalR. And actually, the main thing that we learned it was that SignalR is very good if you want to have a duplex channel open with multiple clients, because it has bookkeeping and it has a backplane on the server side to maintain all the state, and it knows what message it has sent and resends it. It's pretty good, right? That comes with a cost. I'll come to that in a bit. But normally, we just send signals, and then we just measure it, and it says 230 milliseconds. So like 5 milliseconds here, 230 milliseconds to send it, like to get the request and send it back, and we get to reach our goal and be very happy about it, right? We're a bit muckish as well, like yes, we like met this goal. At this point, we know we are scalable as well. Like life is good. We have 1 million daily active users. Like what do we do next? We can just scale up, right? So as I said, we had 1 million and we wanted to go to 70 because that's the amount of load that we already knew that existed in the cloud for Office 365 already. So we say, okay, we go throw money to the problem, add some bunch of machines and scale it up, right? Then it's all good. So we started rolling out and we onboarded more and more bigger organizations, enabled it for that experience. And what happened is that suddenly we started realizing that we had all this bunch of resources, but some of those machines were burning up. Not all of them, but some of them, right? It was very strange. Like, we were like, why is the traffic, like, what is happening behind the scenes for which I have so much of resource, but they are not being used? But some of those VMs are struggling. Their CPU usage spiked till like 80%, it slowed things down. Some of them even crashed and rebooted themselves and then again went to the same mode. It was like chaos. So we kind of rolled back the users and started investigating and say, okay, what is happening here? Remember this thing that we used for SignalR and we were like, yes, we made our performance goal? Turns out it was not a great idea. And what was happening is that SignalR has this thing that because it maintains the backplane, maintains the state behind the scenes, it wants to, like if your connection basically drops, you want to connect back to the same backend server so they can use that state so that it's a bit faster, right? That's an optimization trick. So we had gone and enabled IP affinity in Traffic Manager so that if the connection drops, you reconnect back to the same VM, right? And this actually was the main problem. But to understand it better is that, okay, you have a bunch of users, you have a connection with one guy, it gets reconnected, he connects back. What's the problem? Why do I get all the traffic to the same VM? When we onboarded these big organizations, they all like to be safe and secure. So they are all behind a firewall and a NAT, right? So they have a single public IP. So all this big organization all that traffic came to only one VM. And because of that, even though we had resources left and we could put more money and just add more VMs, it did not matter because you could not vertically scale up the virtual machine. You needed, like, I don't know, a supercomputer to serve that, right? So that model did not work. So we kind of we knew that we had to get rid of SignalR because of this. The other thing I want to mention is that when we were investigating this, we also did a lot of profiling to understand, is it because we are stupid and we are using a lot of resources, somehow there's a deadlock or something, right? It could happen. These kind of symptoms usually means that something goes into a bad state and then that just builds up. And during that, we kind of figured out that SignalR was really using a lot of our resources. It was keeping this backplane. It was doing all this kind of big objects in a heap. They were eating up our memory. Garbage collector was not that happy, and yada, 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 right? So we had to get rid of SignalR for the first reason I explained, but it would be great to reduce the number of resources that are being used. And also remember, to meet our perf goal, we had to have a tunnel. So we kind of like said, okay, SignalR did not scale well for our purpose. Let's go and use WebSockets, right? It's also a tunnel. And it's more simpler, right? You just use a WebSocket. At this point of the project, all our code on the server side, the communication stack was written on SignalR, right? Imagine we are serving more than 1 million users through this communication stack, which is SignalR, on the client side as well. And now we are saying, hey, the engine is running. We need to like change this communication protocol and do WebSockets. Before I say what we did, there's another interesting thing we observed, that even though we had SignalR, for some users, REST was performing better than SignalR even. Okay, this jumps. Yeah, so, and what was happening is that if you looked at people who are using Mac, and using Safari, it happened that their REST requests were faster. I was like, weird, right? Like, why would that happen? And the hypothesis over there was people who use Macs are expensive, right? Like everyone agrees, right? And people who could afford Mac potentially lived in places where the internet connection was better as well. So coupled with internet connection being better, your processing power being better, right? Your overall three-way handshake and everything was more stable. You met your perf goals. You didn't need a tunnel. So we also wanted to have the ability to actually fine-tune and say, okay, for some users which are able to serve through REST, we just do REST. But for others, we want to use the tunnel. Also, you want to also have that capability, because if you try to establish a WebSocket connection, if you fail try many times, you fail, which happens a lot. It doesn't happen a lot, but does happen enough. And if you have millions of users, 1% is a lot. Then you want to have the fallback to REST. REST is pretty resilient, right? But we don't want to. We already have this SignalR communication stack. You don't want to go and build a bunch of 2 more protocols, right? You delete one, you add REST, and you add WebSockets. That's crazy. So what we did is that we said, why don't we just do REST over WebSockets? So what that means is that we wrote 2 layers, one on the client side, on the server side, where the client would just send requests through that layer, but they would send a REST request, right? Send a REST request. What that layer would do, take that REST request, pack it into a small frame, and then send it over. And on the other side, it would just unpack it and then just replay it as a REST request. So all my server needed to understand was a REST request. All my client needed to do was always send REST. But we could fine tune it and say, but it goes through a tunnel, or it doesn't go through a tunnel now, right? So we had those knobs. This is something we're trying to open source. I think it might be useful for some people, but we haven't done that work yet. But I think this really helped us, and it reduced the cost on our servers, and actually helped us come to a cleaner communication stack, which is just REST-based. So when a developer comes and adds a new feature, they just have to worry about one communication stack. Good. Then all was good. We started rolling to more and more users. That means more and more features as well. People started saying, oh, I want Teams data to show up here. I want like chat to show up here, because that's important for me when I want to contextualize someone, right? And then as you become successful with your feature, it grows. Naturally, your code base grows, the number of engineers that's working on it grows, and the number of teams that you work on that project grows. For us, we started with like a couple of people, like 2, 3, and then it grew to almost 50 plus people actively working on the same code base today. And the teams, like it was one team owning everything, and now it's like 8 plus teams working across different time zones, like from India to like Redmond to Europe. Yeah, so there's also a coordination factor. And we knew from day one, we had the luxury that we knew that we will reach to that point if we do things right. So that's a unique position to be in, right? So we could actually think about, how do you want to structure our code? Do you want to just like build it and then see what happens? Or do you want to do microservices, or do you want to do monoliths? Like we were pretty good at doing monoliths. Like I guess everyone would admit that at least Microsoft historically has been very good at doing monoliths. Like companies like Uber and Netflix has pioneered microservices. It's also great, but it has pros and cons. So let's look at one way to do it. One way to do it was just build another monolith with this layered architecture. You have your view model, you have your business layer, you have your storage layer. So I guess everyone's familiar with monoliths, right? So I don't want to go into pros and cons. You guys are good? Yeah. But high level is, it actually is a very simplistic model. Doesn't matter, it's pretty big, as long as you can deploy it often. In many cases, which you can do, if you have a CI/CD pipeline, if you have built the right test, you can actually deploy it very often as well. It doesn't have to say, oh, it's a monolith, it's big, so you have to deploy it once a week. I think that's kind of a myth. A lot of companies have that problem because they grew over time and they do not have the right set of tests and pipeline to be able to do that. But if you're building something from scratch with a monolith, you can go and build that, because you have to do the same thing if you build another service, right? There's like no difference between writing a small service and a big service. What is different, however, is how you structure your code. Okay, this again jumped. Okay, let's go through this a bit slowly. How you structure your code here is that this is layered architecture. And let's say that you want to change something in one of the business logic. You have to go into all these layers and kind of change your data a bit, a business a bit, your controllers and views a bit, right? And the things that change together often are spread across these layers. There was a very good talk from Jimmy Bogart maybe yesterday on vertical scaling that talks a bit about this problem and how you can solve it. We did something very similar, so I'm going to talk about it a bit. On the other hand, you could actually, like for us, we knew that we were going to grow. We will have more teams. So one of the appealing things was, okay, what if we did microservices? Then we could like just say each section of the card is one service, and it's just like one team dealing with files, one team dealing with emails, right? And that would be a great way to scale up more in teams and engineering teams. We also saw the pitfalls of microservices, right? Because we're like a big company, we have done this many times. And we know that without the right set of tools, right set of abstractions, and right set of patterns up front, you will not be successful in this journey if you are just a small team of 3. So what we did was something in between, what we call organized monolith. So it is small pieces of microservices, if you will, but they are not deployable independently. They are not scalable independently. However, they have the same properties. They have bounded context. They deal about only one domain. So all your code about one domain is in the same place. So we want to go and change something file related, you just go to that project. Everything is there in one place. And most importantly, they communicate with each other through a standard communication stack. You cannot just like take a dependency on another project and say, oh, I just like use it, right? Because that basically mangles your code again. Eventually you get spaghetti. So it's very important if you want to follow a structure like this that you make sure that the components that you build, which you aspire to mature into microservices later on, that they communicate well with each other. And also, of course, if you want to follow some of the good principles of microservices, you go and build these blocks so that they own their own data, so that if there is a data that this block owns, another person cannot directly access that data. You have to go through him. So you do those kind of principles. So you're just doing microservices in a fashion without getting the benefit of having to deploy them independently. Maybe that's good for you, or you are not able to scale them independently because they are all in one service. We take all this, it's one service, it's deployed once. This model kind of was very appealing for us because we kind of said, what do we want to achieve as a team? And I think this is a question you have to ask. If it is that you want your individual teams to deploy fully independently, and that is what autonomous means for you, by all means, maybe microservices are great for you. But if your end goal is that all these services are powering the same experience, and I don't, like as long as you can deploy 5 times a day or with every commit, like why do I care if I deploy it or it gets deployed automatically, right? In many cases, we build microservices, and then at the end of the day, we do Docker compose, and then we say, oh, because these are all together, so we want to like deploy this together, or I want to test it together. So you eventually end up coupling some parts of it anyways. One of the good things about microservices that I actually really like is that because they are domain-oriented, it's very easy to go and delete something. Like you can just say, oh, there's no traffic on this service, just delete it, right? In this world, like in the left-hand side world, in the monolithic world, like how many people dare to go and delete a domain, full domain, right? Like because it's a bit hard to go into all these places and reason over it, if you don't have overview, you don't do it. So it just grows. It has more dead weight. In this world, if you are really a good citizen, it's very simple to understand what you can delete. And this good property actually follows in organized monolith, right? Now you have this structured code where you have your entire domain in one place. You can just go and delete it if it's not being used. You can see the telemetry, and then you can delete it. So if you look a bit on how we did it, and you talked about this middle tier service which does all this magic, right? So we fragmented it into smaller things or blocks, if you will. We call them provider services. I think the naming is a bit wrong because they're not really a service, but they are providing a service inside this big block, right? That's why we call provider services. And they own their own state. They have clean communication channels, and they have the same ones. It's standardized. And each part of the card is being served by one of these blocks. So it's a very nice model. You can imagine that you could have built smaller microservices which power each of these services. But then we kind of just, instead of building separate services, we structured in this way. These are all DLLs, but then they're wrapped as one big service. If you want to call it monolithic service or you want to call it organized monolith, it's up to you. And as I said, like I go and say, oh, this LinkedIn thing is not used anymore. You just like delete it, right? And this is where the power of immutable services come, or immutable blocks come. That sometimes you can even go to the extreme and say, hey, somebody wrote this block, he had some domain knowledge, it's very buggy. Just go and rewrite the block because it's very cleanly separated. So if you can rewrite the block and run the same tests, just throw away the other one, right? Make them small so you can do that often, and you can groom. Your developers can change, your teams can change, code can change, but over time there will be. Some of the things which you cannot do with an organized monolith, because you are essentially in the same stack, so you have to use the same technologies, right? One of the other appeals for microservices is that, okay, you could use different tool sets for different services, which is actually useful in many cases. Just an overview of what it means. If you have one of these building blocks, they are formed on bounded context. They should be very simple and small. They should have data ownership. I think this is absolutely mandatory, or else you end up in the same place as before. And you should thrive not to have type dependency on each other. You can depend on each other for functionality, but through a well-established protocol. You can achieve that in many ways. As I said, like Jimmy Bogal like showed in his vertical / architecture. How many of you attended that talk? Okay, like half of you ish. Where he kind of like showed how to do something similar. And what he did is that if I got him properly, he actually implemented the mediator pattern in C#. Or that's a pattern where you can build building blocks, but they don't depend on each other. They go through a mediator to actually consume its functionality, right? So you could use that. But what we did was all these blocks, all the interfaces for these blocks were pulled out into a common place. So if anyone wanted to know, I want to consume files because it's a dependency. You don't depend on the files provider service. You depend on that interfaces project where the interface is there, and then the implementation gets injected for you later on at runtime. What this gives us is that if you have this nice abstraction, later on it's easy to move to another communication protocol. You can just put a REST on top or do whatever, right? Yes, so if we look at our project structure, it's something like this. You have these provider services, you have like shared libraries, and I think I haven't talked enough about shared libraries. When you venture into the world of microservices or organized monolith, it's super important to have the cross-cutting concerns figured out, like your auth, monitoring, logging, bunch of cross-cutting concerns. For us, caching was a cross-cutting concern because all these blocks would cache, right? Or if you want to talk to storage, the same thing. So you have to like figure those out, and all the provider services will use these libraries, standardized, right? And then if in the provider service block you have bunch of this, so people just came, all they had to do is create a project, say that this is my domain, use those libraries, build their domain, and then just be done with it, right? And then don't forget about deploying and everything. It just happens out of the box for you. Of course, you have to own the endpoints that you have for your provider service so that you are accountable for that. There's alerting and everything that you own. But when you want to reason about one part of the code, you come to that particular project based on that domain. And the last part of this is that, as I spoil it by saying, is that you could actually take one of these blocks out and you can make them into a microservice very easily for two reasons. One is that it's already formed with the domain in mind. So that was what you would have done if you wanted to create a microservice from the beginning. And it also gave you an opportunity to understand if your service boundary is proper, because you are in this world, you're learning, you actually refactor the code many times and you get your boundary right. At this point, you're pretty stable to actually spin this up as a microservice. All you need to do is the communication protocol you had, switch it to REST, deploy it as its own service, and done, right? Of course, done means start off another journey because now you're in a microservice world. So it's a new journey that you start. But you have delayed that journey. Because I often like talk to many startups and they share a lot of very interesting stories about what they did on how to test microservices or how to run them, how to standardize them. And they have these great stories, and it's actually admiring to even hear the stories. But if I go and ask them, like, why did you even start with microservices? Like, often people say, I don't know, like, it was like that, right? I think a lot of this has to do with hype and not business requirements. So what I'm trying to say is that try to understand your business requirement. It could be that you need to go to microservices, but you could start with an organized monolith. in our case, it has helped us. So that is an option to consider as well. Of course, you can do more of this, and then you can actually just build one which is completely new using the same standards. How am I doing in time? Okay, good. So key takeaways. We talked about scaling, we talked about performance, and we talked about scaling code bases and engineers. The key takeaway for scaling architectures is that every resource that you have in your architecture needs to be scalable on its own. That is the only way to achieve true scalability for your architecture. If one of the pieces, like for us, Signal R, we didn't even think about it as a resource, right? But it was a fundamental resource. That was a resource that we were using to communicate with services. That was our bottleneck. Right. And then think about scaling just broader than this PC or data center, like just go more and more. The second is designing for performance. Like we talked about some examples, like, oh, we did this, and then we fine-tuned this because this was slow. All of this was just possible because we were able to measure it. We had optics. I think that's the key takeaway. You want to like design for performance, you need to have visibility on every part of the stack, from where your request starts, from the browser, where does it hit a traffic manager, then it goes to a load balancer, it goes to your VM, it goes to your process, it goes to your thread, then it like goes to another service. You know, like the more visibility you have, the more you will know what you can do, the trade-offs that you can do to make it performant. You need to understand it. So there's a very famous, or maybe it's not that famous, but I really like this saying from Peter Drucker, is that you can't measure it, you can't improve it. So like designing for performance, for me, this quote sums it up. Like if you can internalize this code, then you can actually really design for performance. If you can know, you can measure everything on the way, then you can really find the ways. And your way would be completely different because your scenario is very different. So the takeaway is make sure that you understand and have enough optics early in your project. The third thing is that scaling engineering should be considered as a first-class problem. Often, people don't think about this upfront, right? We kind of like start with this, oh, I want to build this feature, I want to have this business, but if you want to build a long-lasting business, a long-lasting product, you need to think about your engineering, how will it scale? I think like companies like Uber and Netflix has reflected a lot on this because they kind of knew that they were growing super fast, and there was no way they can have like a huge monolithic application which would scale to their needs. Most often, people don't have that problem. But you could also think from your code structure point of view. I think like the code architecture is as important as your overall resource architecture or your topology on how you manage your resources. And it doesn't have to be binary choice between, oh, I just build a monolith or else I just build a microservice and take this headache. It can be that you start with an organized monolith, and then as you mature more, you go and as you mature more, you go and actually build into microservices when you have the right set of tools, right? So it doesn't have the binary choice. So that was all I had for today. Thank you for coming and listening, and I'm here to take some questions if there are any. Yes?
You mentioned something about prefetching the data and caching it to boost the user experience and performance, right?
Yeah.
So what if I prefetch the data, cached it, but within the next 1 minute, the query performance gets changed in HR system?
Yes.
So how would you actually remove it?
Yes. That's actually a very good question. I think there was a talk where they said like one of the two hardest problems in the world or in computer science was distributed systems, and one was cache invalidation, right? So you're talking about cache invalidation, right? Like when the cache data becomes stale. I think it's a very hard problem to solve. We are thinking of solving it for our services. We are trying to build hooks back from our data sources so that when anything changes, we can push it up to the cache and say, okay, this data is stale. You have to go and refetch it, right? But so far, we haven't done it. And it seems that without even doing that, we have a good enough experience. Because what we did instead is that we looked at all the data and said, if the data it needs to be fresh, we don't cache it. We take the performance hit. For example, in the card, you actually have emails. So it shows you the last 3 emails that we have interacted with if I'm looking at you. If I send you an email and then immediately in your inbox you have me and you hover on me, you will not see that data if you had cached it. Right? So then that's a bad experience. So you have to like go scenario by scenario and decide does it make sense to cache? Is it stale data good enough for your scenario? If it is, then you cache it, and then you have like time to live, so you can tune that. How long is it good enough, right? So I think the answer here is that it depends on your scenario. There is no magic or silver bullet for this. It is a hard problem. We are aware of it. For some cases, it's important for us to do caching validation. That brings with it another set of scaling challenges, because if you had all these updates happening downstream and you want to push all this up to your cache, that's another infrastructure that you have to build. Yeah. Does that answer your question? Great. Yes?
How are you managing transactions and rollbacks when there is actually microservice to microservice calls?
Yeah.
Say microservice A calling to microservice S,
Yeah.
but one has already been called, but second has failed. So
Yeah.
rollback was
Yes. So I think this also comes back from the same microservice principle, right? Like when you write your code, you need to just assume that all your dependencies can fail, right? That's the first assumption. And this is like a different mindset of programming, because like we historically started with monoliths where everything was in the same in process, so nothing failed. But now all your dependencies will fail, so the way you write code is different. It's just, so for us, what we do is that we look at what it's supposed to do, what kind of data it should give. Like for example, it tried to fetch the cache, let's say, and the cache failed. Then what can we do? We can say that, okay, we couldn't get it. So the person who called can take a decision that it's fine for me not to serve this experience at this point, right? That portion will go down, for example. And because we are also cache-based, we are able to tolerate some of the cache misses and some of the data loss, so the experience doesn't suffer that much. So we didn't have to solve very strict transaction kind of problems that some of you might have. Yeah. Any more questions? Yeah.
And a question about authentication across all these services.
Yeah.
Like how you showed from the card to all of this, all of these services.
Yeah.
Who's doing the authentication?
So we have, because this is one service, right? And then you have all these smaller blocks. That one service has, we use the ON request pipeline. So there is a module which does authentication. How I envision when we extract them into microservices would be similar, that we will have an authentication service upfront. Instead of it being a middleware, it will just be a service, right? With a gateway. So for now, it's our gateway is kind of, if you think about it, it's the request pipeline, right? Everything goes through that. So you just put an inbound authentication there. Cool. Is there any other questions? If not, thank you very much for coming and listening, and I'll hang around so we can also discuss if there are more questions.